they know what code smells exist in their code, and if they know the correlation between the code smells and vulnerabilities, they can easily identify or locate the vulnerable program components in their software. So that's why we are mainly interested to identify some correlation, significant correlation between the code smells and software vulnerabilities. So first of all, I'd like to give a brief description about the code smell. The term code smell was first coined by Kent Beck. He said a code smell is a hint that something has gone wrong somewhere in your code. So it means code smell is not the problem itself, but rather it is a kind of sign, or it's a kind of indication that some deeper problem can happen or might occur in future in your code. So according to Martin Fowler, a code smell is a surface indication that usually corresponds to a deeper problem in the system. So in summary, code smell does not indicate that your program has the problem, but it indicates that your program might face a deeper problem later if you don't fix the surface problem now. So that's why to identify code smell and to get the correlation between code smell and software bugs or security bugs is very important for the developers. So to get a better understanding of code smell, I'll give some examples of different types of code smell here. First example is called the long method. So for example, if your function or in Java, it is called the method. So if your function or method is too large, it will be like a large burger, which will be hard to digest and which will make your testing effort harder. So if your function or if your program component does lots of responsibilities at the same time, it would be very inconvenient for the programmers and also for the user. Another type of code smell is called the duplicated code. Duplicated code happens when you repeat the same piece of code or same coding structure at different parts of your program. So what is the problem of duplicated code? The problem is that, for example, as a programmer, you have fixed an issue in one part of your program, but you forgot to fix the same issue and in the other similar parts of your program. So actually it will not solve your problem, rather it will create some further problem in your program. So that's why duplicated code is also not expected by the developers or the programmers. Another type of code smell is called the large class. Large class contains many data fields, many functions, lots of lines of code. So just like the long method, if your class is very large, if it has lots of responsibilities, then it will be very difficult for you to manage it, and it will be a very complex class too. Another example could be the feature envy. Feature envy is a type of code smell. It happens when your function or a particular function of a particular class depends on other function or on other classes more than its own class. Then what happens? The interaction or the dependency among the functions or among the multiple classes become higher. And if the dependency or interaction becomes higher, coupling will be higher, and always high coupling is not expected. So it will create many type of problem. So these are some good examples of code smell. So the research goal of our work was basically to investigate the relationship between the presence of these type of code smells and software vulnerabilities. So to reach that goal, we have formulated two research questions. In the first research question, we said, what is the relationship between smells and software vulnerabilities? So in this research question, we basically focused to find out the general relationship between the code smells and software vulnerabilities. Here, we did not differentiate the types of code smells or the types of vulnerabilities. But in research question 2, we try to identify, are there certain smells that have more or stronger relationship to vulnerabilities than others? So here we basically focused on different types of code and architecture smells to find out those smells that could have a potential stronger relationship to vulnerabilities compared to other smells. So the code smells that we have considered in our study are got class, lazy class. So all of the code smells that we considered in our study has been listed here. So the reason we chose or selected these code smells in our study basically was twofold reason. One is in the most of the earlier studies, researchers used these type of code smells in their studies for getting the correlation with different types of software bugs. And second reason was that we actually tried to select those common code smells and architectural smells that were proved to have some negative impact on software quality. So these are basic two reasons why we chose these code smells. And we used our custom built code smell detection tool called GetSmell. So using that tool, we tried to extract all these code smells from the source code. The systems that we used or studied for our research are Apache Tomcat, Apache CXF, and Android. So we used 3 major releases of Apache Tomcat 6, 7, 8, 2 major releases of Apache CXF 2 and 3, and 2 major releases of Android 6 and 7. And around in every, here is the list of number of total classes in every version that we used here. So around we used in total 59,000 classes, 721,000 functions, and around more than 12 million lines of code. From here we try to detect the code smells and vulnerabilities. So another reason, one reason of using these type of systems in our study was all of them are open source, and they have the public security advisories in their website, which was very helpful for us to collect the software vulnerabilities. So this is a picture, a brief picture of our study design. If you see the picture, there are 2 parts basically. One is extracting the code smells. Another one is extracting the vulnerable and non-vulnerable or neutral classes. We term it as neutral class because we cannot say them non-vulnerable because maybe the vulnerability has not been exposed yet, but we cannot certainly say that they don't have vulnerability. So for that purpose, right now we have termed them as neutral classes. So from the source code repository, using the GetSmell tool, we detected the smelly artifacts and the non-smelly artifacts. And from the publicly available security reports, we extracted the vulnerable classes and non-vulnerable or neutral classes. Then we did some data analysis and identified 4 types of classes: smelly vulnerable classes, smelly neutral classes, non-smelly vulnerable classes, and non-smelly neutral classes. Then on these 4 types of classes, we did some statistical analysis to find out the significant relationship with the between the smells and vulnerabilities. So here is the result of our first research question, where we tried to identify the relationship between smells and software vulnerabilities. So if you see this table, there are 4 basic columns: smells and vulnerability, no smells and vulnerability, smells and no vulnerability, and no smells and no vulnerability. That means these are the numbers of classes where we found either smells we found both smells and vulnerability, or we did not find neither of them. So this table indicates basically the result that we did after the statistical analysis. So for research question 1, we employed the Fisher test. So Fisher test is basically a kind of non-parametric test, and we saw that the p-values of Fisher test are not basically interpretable here, because there is one column where we found that all of the rows are zeros, like the no smells and vulnerability. That means we did not find any class where the vulnerability exists, but any smell does not exist. So in order for interpreting our result, we then employed to find the odds ratio, which is another measure where when the odd ratio become greater than 1, that means it shows you high likelihood of getting an outcome based on an exposure. But if your odds ratio becomes less than 1, it means there is no likelihood of that event to occur based on the exposure. So in our case, we got odd ratio higher than 1 for almost all of the versions except Apache Tomcat 8 and Apache CXF version number 3. So that means there is a high likelihood that vulnerability will exist if code smell exists there. In our second research question, which was, are there certain smells that have a stronger relationship to vulnerabilities than others? Here we saw that there are some smells which had significant relationship with vulnerability. For example, got class, complex class, large class, data class, and so on. And there are some smells, mostly we got architectural smells like hub-like dependency, class cyclic dependency, unstable dependency, which had no significant relation with vulnerability. So some important keys, some important takeaways of our study is that first one, we found a good relation between the GOT class, large class, complex class, and software vulnerability, and that finding was also supported by Cairo et al., which is a previous study on finding the correlation between vulnerability and between the software error and the code smell. And we also found the relation of feature envy with software vulnerability, which also supported by another work by Gradisnik et al. And in their study, they also found that feature envy is expected to be correlated with low quality code. So this conclusion actually supports our claim. So we know that feature envy hampers encapsulation because when feature envy happens, the function of a particular class will be more interested on the function of other class. So it is very important for doing the security leakage or security breach. So feature envy can have a good relation with software vulnerability. And in Apache Tomcat, we found that this kind of smell, we found this kind of smell in 68.3% of the total vulnerable classes. Another important message of our work was that we got a good relation between data class, refused bequest code smell, and software vulnerabilities, but in earlier studies, they did not find any relationship between them. So we think we can do more studies, further study on these two types of code smells. So how our work differ from others? In our earlier studies, they mostly focused on security smells like outdated library, weak crypto algorithm based security smells. But in our work, we try to focus mostly traditional code smells and architectural smells. In earlier studies, the researchers extracted the vulnerability by using static analysis tool. But we know that most of the static analysis tool, they have lots of false positive. That's why we actually try to avoid using static analysis tool. Rather, we depended on the publicly available security advisories. And another important difference is that in some of the earlier studies, they considered specific domains like Android application or GitHub Python gist. But in our paper, we mostly focused on the Java applications, and we did not consider any particular context or infrastructure like this. So the important contribution of this work for the practitioners, we think that it will help them to detect the vulnerable area in their coding in the early phase of development, because if they are aware of the code smells, they can easily detect software vulnerability or any possibility of security leakage in their program in the early phase of development. Another important contribution is that it will reduce the testing effort or testing resources or testing load during the testing phase of software development lifecycle. And finally, it will help us to build a vulnerability prediction model based on the code smells. So in summary, we tried to determine the significant relationship between smells and software vulnerabilities, and we tried to present a set of smells that could have potential statistically significant relation with software vulnerability, and some smells for which we did not get any significant relation, and we hope that in our future work we will do more study on them. So in our future plan, in this study, as we did not consider different types of vulnerabilities like denial of service, SQL injection, cross-site scripting, in our future work, we'll try to focus on different types of vulnerabilities to consider other confounding factors like the complexity of different classes, the quantity of distinct smells, and finally, we have planned to develop a vulnerability prediction model using the code smells. So here is the replication package where you would get the data set we used and other files. And here's the contact details. So if you have any question, you are most welcome to ask us and send us email. That's all for my presentation. So if you have any question, I'd really appreciate that. Thank you. Thank you all.
Okay, thanks for your nice talk. So please, if you have the audience, if you have questions, you can post your question in our chat windows, or you can unmute your microphone and ask. And Tang Yuan, you can collect some questions from Slack. Okay. Okay. Maybe I can ask one question.
Sure.
You have mentioned you have, because from the table you present there's some the codes with smell and vulnerable codes just take a very small portion in your database, right? So I mean, so what we can do to help us to find some vulnerabilities in the smelly code, because the both smelly and vulnerable codes just take a very small portion here. So if you only consider all the samples of code, smelly code, it's you need a lot of efforts to to filter out the real vulnerable code. So what's your idea to to refine the results of the code?
So you mean in our table in the first column where the smells and vulnerability, you are indicating that column?
Yes. Yeah, so, compared to the number of the smells and the non-vulnerabilities.
Yes, right. Yes. Yeah, thank you for the question. Yeah, you know that vulnerability is very rare. The vulnerability data actually is very rare, and that's why we sometimes get difficulty to find vulnerability in different types of applications. And another thing is most of the applications, they do not reveal their vulnerable data. And vulnerability is not the general bugs or general software problem. So the rate of vulnerability compared to other general software bugs is very low. So that's why it is very normal and usual that you will find lower number of vulnerability in the entire code base. So that's why we tried to identify the relation using the p-value. So we use the p-value and we use the non-parametric test and use the p-value because we wanted to know the significant difference of the significant relation of the smells and with the vulnerabilities. So if you consider the p-value and if it is less than 0.05, it actually does not consider those things. You can easily get the significance based on the p-values. I'm not sure if you asked the question. I mean, I answered the question you asked. Is that what you meant?
Dr. Meng, are you able to, we cannot hear you right now. Okay, so there seems to be like a slight connection problem with Dr. Meng. Let's wait for him to reconnect. In the meantime, I see actually there's no, if you have any questions, I think for the authors for the first paper, I think please by all means post, you could post questions in the chat, and you could also post questions in the channel, the Slack channel I just created called Track 2 Questions. If currently there's no question posted here, so could we like move on to the second talk from paper 42?
Okay, so I'm stopping my share. Okay.
Yes. Thank you so much for your great presentation.
Okay, thank you so much. Yeah. Bye.
Dr. Zhang, Yanxin, are you ready to share your screen, please?
Yes. So I'm still waiting for the. Okay. How should I start sharing? Wait. Okay. Okay. Yes. Oh, yes. Can you see the screen now?
Yes.
Okay. Yes.
Please go ahead.
Okay. Yes. Okay. So today I'm going to share my work, and this is regarding the topic regarding the code deobfuscation of the obfuscated Android piggyback apps. So there is some term such as what is the deobfuscation, code deobfuscation, and what is the piggyback app, and I will give a detailed explanation in the following slides. And so first a short introduce to the Android OS. As we all know that the Android OS is already quite popular and actually dominating the markets right now. So basically only iOS can have a competition. However, as the open source character of the Android OS, so it means that it will expose many shortcomings or weak points to the developers, especially for the attackers. Yes. So here this slide shows a very common way that how the attackers will attack Android apps, because for the attackers or hackers, usually they will not create a brand new malware, Android malware of them all, because there is many reasons, but and the first reason is that basically the brand new apps, like their malware, is actually unfamous, and actually they will not. Okay. Oh, okay. Actually, so people will just not download their malware, so they will fail their purpose to make a profit by developing these malwares. So the other strategy for the hackers or attackers is that they will create some repackaged Android malware, right? So what means all the piggyback can Android malware? So what they do is that they just download a normal or famous Android apps, and they will decompile it. So the source code here will be exposed to the attackers and hackers. So what they do is that they just insert some malicious code that will like request more permissions, or request or steal some privacy, or steal some password information from the users. And then after they insert this malicious code, and they will recompile this APK again, and just use the same name to upload to the platform, such as Google Play. So people will download by mis-download, and after they use this malware, so their information will be stolen, right? So people will be harmed. So actually, this way is a very common way. And there's a study that's showing that over 80% of the malware in the Android market is actually being created by this way. Yes, so this is the main way that the attackers will, how they will create their malware for profiting. Yes, so and after that, but so far the antivirus industry has already developed many tools, such as there's many famous antivirus products, such as Kaspersky or VirusTotal, right? And they will check this APK file even before they are installed on the mobile phones. They will check if this APK file contains malicious, if it is malware or benign, right? So, but so right now the attackers, they are becoming more, they're becoming smarter, and they actually take some actions to invade the detection of the these antivirus products. And what they do is that they are actually using the to generate some adversarial samples, or the adversarial variants by using the code obfuscations, right? So the code obfuscation means that, so here is a detailed example of the obfuscation means. So in the left side, it is the original code, right? So, and after obfuscated, it will like change the terms, like the class names or method names into a into some way, for example, for some meaningful terms into a unmeaningful terms, right? So basically, it is a reorganization or reprocessing on the previous on the released programs, and they will change the original program into a new one. However, the function of the code will remain the same. Yes. So by this way, that's the obfuscated code or the obfuscated malicious code will invade the detection of the antivirus products, right? So and also and also there is some studies that have shown that the obfuscation technology will cause a significant decrease in the ability of accurately detecting the Android malware, right? So, so here there is the issue for the antivirus engines and the products. So they want to finding another way to defend the invading technology or the obfuscation technology, right? So so there is a need to defend this obfuscation, more obfuscated malware. And there is already some works that the strategy is called deobfuscation. Yes, deobfuscation to defend the obfuscated malware. And what does the deobfuscation mean is that so usually the obfuscated code will see some unmeaningful words, right? Like the example shown in this slide. You can see the obfuscated code will have some term like GM, OM. The developers or the engineers, if human beings see this code, will be very confused. Because they are not machines, and it will increase the difficulty for humans to understand and to get through the logic of the code. Yes, and also it by doing this way, it will make the antivirus engines effortless, right? So what the deobfuscation means is that just simply to transfer the unmeaningless, the meaningless term in the code into some meaningful code. So if this code, this obfuscated code is deobfuscated, then it will mean that the human beings will see and understand the meaning of the of this code. And people will ask that how they will decide the term, because it's only G, M, and O, J. So how they will decide what's the meaningful word that should be transferred into this deobfuscated code. So the way is that using the data-driven strategy. So basically, it's a model-based strategy. The tool, the deobfuscated tool, will first learn the obfuscated code and also the deobfuscated code. So there is a training set that teaching the related obfuscated code and the deobfuscated code. So once the model is well trained, and then if people feed in some new obfuscated code, it will give the deobfuscated code back. So people will ask that if regarding the Android malware detection scenarios, will this deobfuscated tool will really help that to detect the obfuscated Android malware? So basically, this is a question. Yes, and people, and we would like to make it clear so we conduct a study to figure it out that if this deobfuscated tool, advanced deobfuscated tool, will help the antivirus engines to improve their efficiency against the obfuscated Android malware. So, and here is how we do. Here is the overview of our empirical studies. Yes. Yes. So what we do is that we first have the original Android malware apps. Yes, Piggybacked apps. So what does the original mean is that the original means the Android malware without obfuscations. Yes, without obfuscations. And the next step is that we first obfuscated them using the obfuscation tools, and we obfuscated them. So we'll get some the obfuscated apps, right? We'll get the obfuscated apps. And then what we do is that we use the obfuscation set of Android malwares, and we upload, and we use the different antivirus engines to detect them. Because what we do is that these original piggybacked apps, their detection rate is 100%. Yes, so we have the commercial antivirus engines and also some machine learning based engines. And also we have the similarity detection engines to detect if the two malwares are cloned. So the original Android malware, their detection rate by these detectors are 100%. And we will test that after obfuscation, the obfuscated sets, how the detection rate of these antivirus engines will be tested. Yes, will be changed. And then after that, we will further, take these obfuscated apps and we will de-obfuscate them, right? So then after that, we will have the de-obfuscated Android malware sets, right? And we will use this use the antivirus engines to test the de-obfuscated sets of Android apps and see how the detection rate will be affected. So then we will have collection the data and see how the detection rate will be affected by the obfuscation strategy and the de-obfuscation strategies. So basically this is the process how we conducted this experiment. Yes. And so before we, so first, then we will raise three research questions. The first one is that how the obfuscation strategy will have impacted the precision of anti-malware detectors. Yes, it's the first part of this experiment, of this study. And the second question is that how is the precision of the anti-malware detection impacted by the obfuscation strategies? Yes, is that if once the obfuscated malware is de-obfuscated, and how the precisions will change and be affected. The third research question is that how the different de-obfuscation tools impact the precision of the anti-malware detectors is because when we de-obfuscated these obfuscated malwares, we use two different tools, and we want to evaluate the performance of each tool in the point of the tool aspect, and we'll give a conclusion that for which de-obfuscation tools will have a better performance. That's the purpose of the third of this research questions. Yes. So after that, we first evaluate the first research questions, and we have these obfuscated obfuscation results. And from this table, we can have a look that. So in this table shows the influence of the obfuscation strategies. Obfuscation strategy is that here is the shortcoming of the abstraction of the strategies, and each term represents a kind of obfuscation strategies. For example, the strings here means that the offer to encrypt the string in the code of Android apps, encrypt the strings, and also the permission here means that to encrypt the permission to change the term of the permission in the Android apps. And here here, VirusTotal is a commercial antivirus engines, and these engines collected more than over 60 antivirus engines in this single website. So basically, this is a embedding or ensembling of different commercial antivirus engines. And driving and CSBD needs two well-known machine learning-based detectors. And also the AndroGuard and the SimiDrive means that to detect the Android malware, basically based on the similarity of the two apps. It means that if two apps have a very high similarity scores, means that the one of the apps is malware because it is cloned from the other one. Yes. So we can see that after regarding the commercial antivirus engines, the intuitive idea is that after obfuscations, all the commercial antivirus engines, the detection rate has increased. But
excuse me, Yanxin, could you conclude your work quickly, because we are out of time. Yeah, you please conclude your work maybe in 2 or 3 minutes. Okay, sorry about that.
Yes, no problem. Yes.
Thank you.
Yes, so we have some findings, right? So basically is that the obfuscations will have a very strong impact to invade the detectors, except this one, this strategy actually has helped if people encrypt the string in the code, it actually helped the VirusTotal to detect its Android malware. And this is a very interesting point to find, because it means that not all the obfuscation strategies will help the attackers to invade. Yes, and the second question is that for the code deobfuscations, and here to conclude is that we have found that if people deobfuscated this malware, then some detection rate will decrease, and some obfuscated malware, the detection rate will increase. So we have some medicated detail. However, the conclusion is that not the deobfuscation strategies not help all the obfuscated malware for detection. Some will, but some not. And we have a detailed findings. If people are interested, they can have a look. And the third one is that we have two obfuscated deobfuscation tools, and basically regarding these tools, we have simplified the guard, and we can see that the one of them has some better effects to help the antivirus engines detection rate in some scenarios. Yes. So all the detailed conclusions can be found in the paper. If people have interest, they can find out more. And yes, so basically that's the work. And yes.
Okay, thank you, Yanxin. So yes. Do you have any questions for the audience?
No.
Okay, because we are running out of time. If anyone wants to ask you questions, you can just put the question, put the message in the Slack, or maybe contact you directly. Okay. Okay. Thank you, Yanxin.
Yes. Okay. So I will stop the sharing. Yeah.
Oh, okay. Yeah. So who is will present the third one? Third paper is sorry. Sorry, where's our third presenter?
Hello.
Hey, hello.
Am I audible?
Yeah, I can hear you.
Okay.
Can you test your slides?
Yeah.
Mm-hmm.
Is it visible?
Yeah, you can see it's very clear. Okay. Okay, so
Yeah.
Maybe you can just start. Yeah.
Okay. Hello, everyone. The title of this presentation is Generalized Notion of Non-Interference for Flow Security of Sequential and Concurrent Programs. My name is Sandip Ghosal. I'm a research scholar from Department of Computer Science and Engineering, IIT Bombay, India. This is a joint work with my supervisor, Professor R.K. Shyamasundar. First, I will briefly highlight the contribution of this work. We have developed a concrete model for flow secure execution of sequential program. Also, we have integrated this general security lattice into our program and into the model. Next, we have defined a non-interference for enforcing flow security in sequential program. Our variant of non-interference is compositional at the primitive level of computer operation. And finally, we have generalized the definition of non-interference for concurrent programs as well. The concurrent programs basically communicate through shared variables. We shall start with a brief background on information flow control and information leaks. We have seen several applications for discretionary access control model uh, that basically restrict access to system objects. As shown in this slide, an access control matrix um, where it says that user 1 cannot access the object Y and user 2 cannot access the object X. However, a program having access to both X and Y can transfer information from X to Y or vice versa through various information channels. Information channels can be categorized into three categories broadly: explicit channel, implicit channel, and covert channel. In case of explicit channel, an assignment statement, for example, x equals to y, can leak information from y to x. A conditional branch statement can leak information implicitly from the condition to the target variable of one of the branches. There are several covert channels, for example, termination channel, progress channel, timing channel, power channel. A termination channel, example of termination channel is shown in this example, where the information leak depends on the termination or non-termination of the program. The solution that IFC follows is a mandatory access control where a security policy is attached to subjects and objects of a program, and that security policy is followed throughout the system. Security policies are also called security labels or security classes. Security labels comprises the two following parts: confidentiality policy and integrity policy. Confidentiality policies basically answers questions like who can read my information, and integrity policies answers questions like who has written into this information. There are several security models, for example, decentralized label model, disjunction category model, reader status flow model. A security label as per reader status flow model or RWFM is shown in this slide as Alice, Alice, Bob, comma, Charlie. This means Alice is the owner of the policy, Alice, Bob are the readers of the information, and Charlie is the potential writer of this information. Next, we are moving towards the security lattice. Let SC denote the set of all security classes, and CANFLO2 is a binary relation between two security classes. Then SC becomes a partially ordered set. Further, join and meet are two class combining operators that evaluates least upper bound and greatest lower bound of two security classes. And maximum and minimum element are denoted by top and bottom. Therefore, SC is a universal bounded lattice. Here we have example of two kind of lattice. One is 2-point lattice where there are only 2 points, high and low. Another is general multi-point lattice where there are multiple points. Note that in both the lattices, information flows in the upward direction only. Non-interference is the baseline property for enforcing flow security in information flow control. Non-interference says that changes in high memory part of a system should not be observable through the low memory part. These high and low memory parts can be realized by high and low levels respectively for a two-point lattice. Uh, there are several interpretations of non-interference. Initially, Goguen and Mexico in 1982 coined the term non-interference for flow security. They said two groups of users are non-interfering if the actions performed by one group of users do not affect the observable output of another group of users. Uh, Here is an example like L equals to H are followed by L equals to 0, where H and L are the high and low variable. Suppose a user U1 can access both H and L, but user U2 can access only L. Let the input sequence be U1, L equals to H, U1, L equals to L. That means U1 is executing those two statements. Then the final value of L will be always 0 as seen by U2. The conclusion is that the program is always non-interfering as per the definition given. Um, Later, Volpano, Erwin, and Smith they proposed a security type system as a semantic characterization of non-interference. They say if a source of information flow in a command is given a type tau, then the command is non-interfering if it is typed as tau command. Tau command means that there should be no variable below tau in that particular command that is going to be updated. Therefore, if we understand from this example, while y equals to 0, if the if the command is given hcmd or h command, then there should be no variable updated in that command uh, whose level is below h. But we can see that the level of y is L, which is below h. Therefore, the program is not non-interfering. The next, the Bodol in 2005 extended the type system proposed by Volpano, and he introduced the two system like type and effect system. The effect system comprises two levels: confidentiality level and termination level. Confidentiality level tracks intra-statement implicit flow, whereas termination level tracks inter-statement implicit flow. This kind of program where information is leaked by termination channel can be prevented through this particular interpretation of non-interference. So where are the problems then? Consider the concurrent program shown in the slide where one program is running the statement L equals to H followed by L equals to 0. Another program X equals to L executes concurrently. Now, although the program is non-interfering as the final value of L does not depend on H, but concurrent execution could leak information in H to X. This kind of information leak cannot be realized by the definition given by Goguen and Misigwe, as the definition is non-compositional and only depends on the final value. Next, the type system proposed by Volpano et al. Cannot prevent termination leak that leaks information from loop condition to the following statement. While the type system proposed by Bodol prevents the termination leak, but it cannot realize recurring information flow arise in a loop that is not consistent with the definition of non-interference. In the example shown in the slide, information could flow from X to Z to Y. Further, the existing notions of non-interference are defined with respect to a two-point lattice. However, in real-life applications, it is necessary to adopt a multi-point security lattice. Therefore, our objective is to define a notion of non-interference that is compositional at primitive level of computer operations, and the definition should follow a general security lattice. Naturally, due to multiple points, the non-interference cannot be seen from the perspective of low users only. Therefore, non-interference should be relative to the security level of attacker or attackee. Next, we shall discuss what do we mean by primitive operations. Uh, Consider the language syntax shown in the slide. The sequential part of the language is the syntax of a simple while program, Wait and signal are the usual mechanism for process synchronization, and S1 parallel S2 denotes concurrent composition of two statements. Next, we define the function seq that maps a given statement to corresponding sequence of primitive operations. For this instance, we limit the primitive operations to read and write only. The statement x equals to y plus z is mapped to a sequence read y, read z, and write x. For an assignment statement is x equals to e, where e is a function of y1 to yn, the sequence of primitive operation is defined as read y1 to yn and write x. The input sequence for other statements are shown in the slide. Next, we describe the information state machine. A state machine M is a 4-tuple Q U C delta, where Q is a power set of users U and variables V. A state Q is a finite set of tuples UV. C is the set of commands, and delta is a state transition function. Further, we define the function lambda and gamma. Lambda maps each user and variables to its respective security level from the lattice. Gamma maps each variable V to its value V bar. Uh, Next, we define the information flow policy, or IFP, for a program P. IFP says the program P is secure only if there is no execution of P results in a flow x to y unless lambda of x can flow to lambda of y. And observe the state, we define the state transition function as follows. So for a read variable v, the state does not change if the label of v can flow to user u, otherwise it violates the flow policy. For a write variable v, the state q changes to q prime, whereas the value is replaced by a new value and the label of v is replaced by least upper bound of u underscore and v underscore. An observation of a user u in the state q is defined by the function view as follows. The observation is a set of tuple uv plus or uv minus, where plus means the value v can be seen by u, otherwise it remains hidden. Uh, Next, we define the non-interference for a sequential program with respect to a two-point lattice. Consider an input sequence is as shown here. Let user U1, U2 are labeled as high, and U3, U4 are labeled as low. Then S is non-interfering if for all prefixes X of prefix closure of S, the state transition results in distinguishable observation for the low users U3 and U4. Next, let us consider a general lattice L with n points. Then the input sequence S is non-interfering with respect to user U if and only if the state transition for all the prefixes X of prefix closure of S results in distinguishable observation for U. We shall analyze our definition of non-interference for the program S that leaks information from X to Y with the help of a local variable Z. Let us execute the program S, and B is an attacker. The given level of A and B are on A underscore and B underscore such that A cannot flow to B. Consider X is a sensitive variable that remains hidden to B. Then the initial observation of B is as given here. However, after execution of this particular program, for an input statement S, the observation changes to this one. As the observation changes, as the observation is not equal, the final and initial observation is not equal for a particular input sequence, the program is not non-interfering. Next, we generalize the definition of non-interference for concurrent programs as well. Let two programs S1 and S2 are executing concurrently. and small s1 and small s2 are the corresponding input sequences. Then S1 and S2 are non-interfering with respect to user U if for all possible small S1 and small S2, the S1 and S2 are individually non-interfering, and concurrent execution of X1 and X2 results indistinguishable observation for U, where X1 and X2 are the prefixes of prefix closure of small s1 and small s2, respectively. Next, we shall analyze flow security of the concurrent programs P and Q using our generalized definition of non-interference. Consider user A and B execute the program P and Q. Therefore, initially the variable Y and B remain observable to B. As we can see, that concurrent execution leads to an information flow from Y to X to Y through the shared variable B. The observation of B changes to this one. Therefore, the concurrent execution is not non-interfering with respect to B. So now we are moving forwards to the conclusion and future work. In this work, we have developed a notion of non-interference for sequential and concurrent programs. Our definition of non-interference is compositional at primitive level of computer operations and relative to security levels from a general lattice. The proposed version of non-interference enforces observational equality for all possible complete or incomplete input sequences. For concurrent programs, the non-interference is subject to observational equality for shared variables too. In short, the non-interference for security or insecurity depends on the attacker's observation. In future, we can extend the work by integrating our proposed definition of non-interference with the security assertions for identifying timing leaks in concurrent programs. Further integrating the proposed definition with functional non-interference can help us to achieve a proof system to establish functional correctness and security of the program. Thank you for attending this talk. If you have any question, please let me.
Okay. Thank you, Sandip. So do you have questions now?
Sorry?
I mean, if any audience wants to ask questions, please just
Sure.
unmute your microphone.
Yeah.
Okay, maybe I ask one simple question.
Yeah, sure.
So in this paper, you propose many notations to model sequential or concurrent program, right? So
yes.
I wonder how can we use these notations to develop a more secure software? How we can use these notations?
I'm not able to understand exactly what you are basically asking. So I think what you are asking is how we are basically saying that it is secure for a sequential and concurrent program. Is that right?
I mean, because you define many notations, right? These notations, I mean, in the software engineering, so how can a developer use this notation to, for example, find some security issues or make some...
Right.
Yeah,
right.
yeah.
I have the answer for that. Yeah, thank you. The question is very good. The whatever we have presented for this talk is basically the formalization of non-interference, and we can implement this for any sequential or concurrent language as well. And we have implemented this for Python language. We have basically a platform built on this particular theory, where a subject and object are given labels, and then we are following the properties of non-interference that we have proposed here. And we are saying that whether this particular program is flow secure or not by syntactically checking each statement and checking the information flow policy also. But the underlying property is basically the non-interference what we have proposed in this particular talk.
Okay. Okay, thank you. Okay, if we don't have more questions, so I think this is all of this session. So very nice and impressive talks, and thanks again to our speakers. So everyone we have more questions, you can post a message in our Slack channels. Okay. I think that's all. Thank all.
Thank you.
Yeah.
Thank you
We
for attending this talk.
Yeah. Maybe end the
Yes.
session.
Thank you again, all for your authors and the participants. And the afternoon session will be starting at 2 p.m. Singapore time.
Okay.
Yes.
Yeah. Thank you.